bear with me for a minute. This is not working. Why is this not working? Let's see. This is plugged in. I was having trouble yesterday with another class with my document camera. Now I'm having a different trouble. Let's see. Let's see if we can do it this way. Okay, well, while I'm trying to get this done, we're going to be looking at a completely new topic, which is just about integers, called modular arithmetic and cryptography. So the cryptography part is where we want to make things secret. So the reason I'm pausing is because I've got a new display and it's not playing well with my document camera. And I have no idea why. Yeah, so cryptography is all about hiding information. Now, if I was in the class with you, I would have asked you something like, how many of you have used an ATM in the last, well, I was going to say last week or so, but I suppose hardly anybody's been out to use an ATM. How many of you have used a credit card of some sort recently, either by PayPal or some other secure route? And most people would put up your hands, and I would say, well, congratulations, because you would have used some sort of cryptography in there. Some sort of encryption technique would have been used to encrypt your information to transfer, especially when using ATMs. And I think I mentioned this way back when we were looking at Euclid's algorithm. That was one of the things that actually is built into some of these, or is used somewhere along the line. All of this is going to be done using something called modular arithmetic. And modular arithmetic is modular arithmetic is, if in doubt, turn off the device and start it again. Modular arithmetic is a bit like clock arithmetic. So if I say it's 11 o'clock in the morning and I want to go ahead 3 hours, well, you can either think of it as 11 plus 3 is 14. So what's 14 in terms of time? Well, it's 2 p.m. So 11 o'clock going forward 3 hours, you can either think of it as 14, 100 hours, or you can think of it as 2 o'clock. If you think of a 12-hour clock rather than 24-hour clock. So what you're doing basically is you're converting the number 14 into something that's equivalent in the 12-hour version, namely 2 o'clock. Sorry, I'm just talking here while I'm this document camera goes. So that's, oh, very good. It works. Excellent. Hooray, got to work at last. So just that idea of time using a 12-hour clock is really what we're going to be doing with this thing called modular arithmetic. And now that I've got this working, I can start to share the screen with you. There we go. So you should be able to see that. Can somebody just tell me if you can actually see this, the usual notes? Yeah, cheers, thanks. Right. So I've been blithering on about this modular arithmetic. Basically, think of a 12-hour clock and cryptography as a way of hiding things. Notice that in the next topic, we're going to do something called error detecting codes, and there's a difference between cryptography and codes. And I know in popular language, people think of cryptography and codes as being the same thing. In fact, they're quite different from computer science and mathematics standpoint. So when we talk about crypt, this C-R-Y-P-T is comes from a Latin root for meaning hidden. So this is all about hiding information, whereas codes in this other context, when we get there, I'll talk a lot more about it. Codes is about, in a sense, revealing information. So what's a way of sending information that's transparent, whereas cryptography is a way of transmitting information which is non-transparent, as opaque and as impenetrable as possible. So we're going to be doing this cryptography there. So in cryptography, we've got a message, it's encrypted. So again, crypt meaning hidden. So we're going to hide it or enciphered. And then once it's received at the other end, the person, so you've got a message, you encrypt it to hide it. You encrypt it in such a way that no other third party can read it. And then the receiver receives the encrypted message and then decrypts or deciphers the thing. So, you know, any intruder who looks on can't read it. And a very early example, this is historically what we know due to the Roman military, who used to send messages between the generals and back to Rome, called it's going to be called a Caesar, or Caesar's cipher due to Julius Caesar. It's a very simple-minded thing, but if you didn't know what was going on, it'd be a bit hard to figure out what if somebody just intercepted. It'd be a bit hard to figure out what was going on. Nowadays, it's such an easy thing that kind of everybody knows about it. So the bit of terminology, we talk about plain text and cipher text. So plain text is the data, the raw data, and it could be numbers or it could be words or sentences or whatever. That's the thing that's going to be transmitted, but before it gets encrypted. So it's the raw stuff. The encrypted data, the thing that you actually transmit, is the cipher text. And basically what the Caesar cipher was is, here's another thing. The tradition in this area is that plain text we'll always use lowercase characters, and ciphertext we always use uppercase. So lowercase and uppercase. Actually, somewhere along the line, I'll tell you why they're called lowercase and uppercase. I think it's quite interesting. So the idea is it's a simple substitution. So you want to send the plain text word secret, and how we'll encrypt it is S becomes V. Okay, so S is V. E becomes H, so E becomes H. C becomes F, so there's our F. R becomes U, and then notice E becomes H again. So E is encrypted always as an H. That's actually one of the weaknesses of the cipher. If you do that simple substitution, that one plain text character always gets mapped or encrypted into the same ciphertext character, then that's a very weak encryption technique for reasons which will become obvious in a little while. If we encrypt, then T becomes W. And notice that in this encryption, A becomes D, B becomes E, C becomes F, and basically they've been shifted forward. So we begin with A, then we go B, C, D. So we've shifted forward 3 places. S becomes V, well, S, T, U, V. Again, it goes forward exactly 3 places. And that'll be the mathematics behind it, is this idea of giving a numerical value to the plain text and then shifting or adding something to it. And then that gives you a new numerical value, and then that numerical value gets transformed back into a ciphertext character. Message. Okay, so if you want to send message as a plain text, here's the ciphertext. M becomes P. Notice that E is again H, just the same as it was over here, because we've used the same key. And pictorially, we can think about it this way. This is exactly like this idea of, if I'm at 11 o'clock and I go forward 3 hours, I end up at 2 o'clock. So here's 12, 6, 3, 9, 1, 2, what comes after 3, 4, 5, 6, 7, 8, 10, 11. So if I'm sitting here and I move forward 1, 2, 3, I end up at 2 o'clock. Okay? And you're absolutely familiar with that from very early on in your lives. If I want to start at 3 o'clock and I want to say, well, what's 5 hours before that? Well, I go backwards, 1, 2, 3, 4, 5, and it's 10 o'clock. If I want to start at 9 o'clock and say, what's 7 hours after 9 o'clock? Well, I count forward 1, 2, 3, 4, 5, 6, 7, and I get to 4 o'clock. So what I set up here about moving forward 3 places, we can do pictorially like this. All you're doing is wrapping the alphabet around from A around to Z and then beginning at A again. So we're going to move 3 places in the, well, we're going forward, so in the clockwise direction. So what will, up here, E always became H. So if we start at E, count forward, 1, 2, 3, we end up with our plain text E, ciphertext H. Notice also that another way to get from E to H is if we go backwards. If we go backwards 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So moving forward 3 places is exactly the same as moving backwards 23 places, or anti-clockwise. So we're saying clockwise in the forward or the add direction, and counterclockwise, anti-clockwise in the negative or take away direction. Just like you do with time. It's exactly the same principle. Look, I will say this, in computing, when we deal with binary numbers, you'll do this in discrete mathematics next semester, but the clock face looks like this. There are only 2 numbers on it. And the idea is that if you start at 1, or if you start at 0 and you add 1, well, you do the obvious thing, you go around to 1. But if you start at 1 and add 1 in this system, then what happens? You get to 0, which is really an odd little system. If I start at 1 and I add 4, 1, 2, 3, 4, I get back to 1 again. But if I add 5, 1, 2, 3, 4, 5, 1 plus 5 is equal to 0. Yeah, but you'll see something like that in discrete mathematics. It's really a very important part of what's called Boolean algebra, which is basically one way of dealing with the logic of circuits. So going back to this, when this is this idea that if you start at 11 o'clock and go forwards 3 hours, you end up at 2 o'clock or 14 o'clock. So going back to our clock face, if I start here and I count forward, I say 11 plus 3, I go forward 1, 2, 3, okay, that's 14. And we kind of say to ourselves, 1400 hours or 14 hours and 2 p.m. are the same thing. So they're entirely equivalent. Similarly, if I go ahead another 24 hours, where would I be? Well, 14 to 15, 16, 17, 18, all the way around here, another 24 hours would, another 12 hours, my mistake. Another 12 hours from 14 o'clock would get me to, if I had 12, would get me to 26 o'clock. Okay, so 2 and 14 and 26 are basically the same thing. There's really no difference between them. And that's what this is saying here. When 2 numbers are at the same position, we say that they're congruent. So here on this 12-hour clock face, 2 o'clock, you can't see that, 2 o'clock, 14 o'clock, 26 o'clock are all congruent. That's supposed to be, shouldn't write the margins. Now suppose you've got a 7-hour clock. Okay. We're going to do something just slightly different here. Okay, so I just realized, yeah, we'll do it this way. So with the 7-hour clock, we've got 7 spots around the dial. The only tricky thing that we're going to do, so 7-hour clock, the only tricky thing we're going to do is we're going to start with 0 and move around to 1, 2, 3, 4, 5, 6. And what happens next? What happens after 6? We get to 7. What happens after 7? We get to 8. What happens after 8? We get to 9, 10, 11, 12, 13. And then what happens? We've got 14. Now, I kind of said, well, let's start with 0. I could have started with 1 and gone 1, 2, 3, 4, 5, 6, 7. And that would have been perfectly okay. But then notice that if I start at 3 and I go backwards, I go 3, 2, 1. What happens if you're going backwards from 1? Well, we get to 0 because you're subtracting 1 as you're going around this way. So 3, 2, 1, 0. What happens before 0 if you subtract 1? Well, you get -1 and -2, etc., etc. So it doesn't really matter whether you start at 1 or 0. I tend to think of starting at 0 and then moving around. But just remember that 7 and 0 and 14 are all the same. And we say that 14, 7 and 0 are congruent to each other. 8, 1 are congruent. 9 and 2 are congruent. 3 and 10 are congruent. So we'd write this out as 3 is congruent to 10. And to say that we're working in the 7-hour clock face, we talk about mod 7, which is short for modulus. It also means, if we count backwards, 3, 2, 1, 0, -1, -2, -3. This is also -4. So -4 is also congruent to 3 and 10. And we use this triple equal sign for the congruent. 10 is congruent to 59. Well, if you had to, you could start at 10 and you could count around 10, 11, 12, 13, 14, 15, all the way around until you got to 59. That'd be perfectly okay. You could do that. And if you did, you would in fact find that 10 and 59 are congruent to each other. So the modulus is the number of hours. We've got 1, 2, 3, 4, 5, 6, 7 hours on the clock face. And there's a whole subject in mathematics called number theory. And this is one of the basic, I mean, you could just study these things, you know, for a whole semester or a whole year or a whole lifetime. We're just scratching the surface in terms of the terminology. But this kind of thing is called modular arithmetic, because really what we're doing is we're sticking to arithmetic that just deals with 0, 1, 2, 3, 4, 5, and 6. They're basically the main numbers. And since 7 is congruent to 0, it kind of acts the same. So we don't really have to think about 7. It's really the same object, just given a slightly different name. So this whole field is called modular arithmetic. And the trick here is that we say that two numbers are congruent, modulus a particular value, if the difference between these two things is a multiple of that. So when I said that 10 is congruent to 59, modulus 7, okay, why is that true? Well, you take 59, you subtract 10, and you get 49, and that is equal to a multiple of that. If I say here 1/8, what happens next? 15. Okay, 1 is congruent to 15 mod 7. Why? Because 15 minus 1 is 14, which is a multiple of 7. So we take our 7 and we figure out does 7 divide into that difference? Okay, here I've written as 14 is divisible by 7. I tend to think of it as a multiple of 7. Now, 44 minus 13 is 31. Now, 31 isn't divisible by 6. So we're starting to answer here this question. Is 13 congruent to 44 mod 6? Sorry, I just skipped over that one. Is 13 congruent to 44 mod 6? Well, the answer is no, because you take 44, you subtract 13, you look at the difference, you get 31. And 31 is not a multiple of 6. In fact, it's one more than a multiple of 6. So 13 is not congruent. 13 is not congruent to 44 mod 6. So this statement is not true. In fact, what we would write is, I was just about to, 13 is not congruent to 44 mod 6. Okay, well, now let's do this one. 5 is congruent to 17 mod 6. Well, that's true. Why? 17 minus 5 is 12. 12 is 2 times 6, so it's a multiple of 6. So, yep, that's true. So if I give you 1 minute to work out this one, work on that one, is that true or false? Okay, let's have a look at that one. Is 32 congruent to 68 mod 9? So you simply write 68 minus 32 is 46. And if I've got my arithmetic correct, 36. It was jumping up and down. Sorry, I've got my face away from the camera. Oh, yes, I've got a thumbs up. Thanks, Dale. Yep. So 68 minus 32 is in fact 36, and 36 is 4 times 9. So this is a multiple of 9, or if you like, divisible by 9. When we say divisible, of course, we mean divisible without any remainders. So therefore, 68 is congruent to 32 in the mod 9 system. Now notice that that's also the same thing as saying 32 is congruent to 68 in the Mod 9 system. Why? Because 32 minus 68 is minus 36. Is minus 36 a multiple? Oh, you can't see. 32 this side and 68 that side. Do 32 minus 68 is minus 36. And is minus 36 a multiple of 9? Yes, it is. It's negative 4. I'll write it out that way. So it's still a multiple of 9. Still a multiple of 9. So what this is showing is that it doesn't matter which way around you write this, 68 congruent to 32 or 32 congruent to 68. They're both acceptable. Why? Because one difference is positive, one difference is negative, but they're still both multiples of 9. So a little bit more generally, okay, so that's really what was said here. If A is congruent to B, then B minus A is a multiple of N. So A minus B is also a multiple of N. It's just the negative multiple. Just like here, 68 minus 32 is 4 times N, but 32 minus 68 is negative 4 times the N, times 9. So here's our 7-hour clock again, written out a little bit more neatly, starting with 1, 2, 3, 4, 5, 6, 7, or counting backwards, let's say 7, 8, 9, 10, or counting backwards, 1, 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8. So we've got all these numbers are congruent to each other. All these numbers are congruent to each other. And if you start thinking about this, what is common to all these numbers? Basically, they're all multiples of 7. So 0 times 7, 1 times 7, 2 times 7, 3 times 7, 4 times 7, minus 1 times 7, there's a minus 14 in here, minus 2 times 7, and so on. So all these multiples of 7 are congruent. What's common to these? That's 1 more than 0. 8 is 1 more than 7. 15 is 1 more than 14. Minus 13 is 1 more than minus 14. So all of these numbers here, which are congruent to each other, have the common property that they are 1 more than a multiple of 7. These guys, okay, they're all 2 more than a multiple of 7. Okay, so 9 is 2 more than 7, 16 is 2 more than 14, 23 is 2 more than 21, and so on. These are all 3 more than a multiple of 7. These are all 4 more than a multiple of 7. These are all 5 more, and these are all 6 more. So in a sense, what we're starting to do is pick out 0, 1, 2, 3, 4, 5, and 6. So we're just doing 0, 1, 2, 3, 4, 5, and 6. And we're picking those out. And what we're going to do is reduce each one of these. So reduce 22 to 1, reduce 23 to 2, reduce 24 to 3. 26, where's 26? 26 to 5. 26 is congruent to 5 mod 7. 5 is the smallest number, smallest non-negative number that's congruent to 26. So you look at all the non-negative numbers, so you don't worry about -9, -2, 5, 12, etc., etc. What's the smallest one of these that's congruent to 26? Well, 5 is. Or another way of saying that is what I was starting to get at before. We're looking at the remainders. So another way is these are the remainders when dividing by 7. So if I say to you, what's 23 divided by 7? You'd say 23 divided by 7 is well, it's 3 with a remainder of 2. And what we mean by that is that 23 is a multiple of 7 plus 2. 9 is 1 times 7 plus 2. 16 is 2 times 7 plus 2. So you can think of it either as what remainder you get when dividing by 7, or what's the smallest non-negative number that's congruent to, let's say, what we're doing here. So if we've got 23, what's the smallest non-negative number that's congruent to 23? Well, you look at it and say it's 2. So it's kind of two different ways of looking at the same thing. I tend to think of things using this remainder. And so what we say is that 26, where are we? 26 is congruent to 5, or can be reduced to 5. 23 can be reduced to 2. 10 can be reduced to 3. Sorry, I've just lost a page. Okay. I don't know where my page got to. So here's another example. If you want to reduce a number modulo another number, so remember that's the size of the clock face there. We want to find the number r, think of the remainder, where r could be 0 or above, and r is as small as possible. So if I ask you to, well, actually, let's see if you can do that without looking at the whole thing. So if I ask you to reduce 86 modulo 11 without doing the clock face thing, you would do what? So I'll give you maybe a minute or so to think about that one. Okay, I'll give you another 30 seconds. Okay, there are a few ways of doing this. Some are more tedious than others. Some of the obvious way would simply be to start with one that we're doing modulo 11. So 1, 2, 3, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, I can't count. 10, 11, 12. Okay, 13, 14. You could keep on going around and round and round until you got to 86. That'd be one way of doing it. Another way of doing it, we're doing reduce 86 mod 11. Another way of doing it is to think, oh, 86 minus 11 is 75. So wherever 86 appears on the clock face, it'll be congruent to 75. So 86 is congruent to 75 mod 11. But 75 is still pretty big, so you might say to yourself, oh, 75 minus 11 again is 64. So 86 is congruent to 75, is also congruent to 64 mod 11. And you could just keep on going down, and that'd be another way. Well, in fact, yeah, okay. So that's actually what's happened in this. So let's just subtract 11 each time. 86 minus 11 is 75. Minus 11 again is 64. They're all congruent. Minus 11 again is 53, 42, 31, 29. And if we subtract 11 here, then clearly we'll get negative something. So this is the smallest number which is congruent to 86, which is still positive or 0. So 86 is reduced to 9. The other way, the third way that you could do this is you think to yourself, I'm really after the remainders. So what's the biggest multiple of 11 that goes into 86? Well, the biggest multiple, so what are the multiples? There's 11, 22, 33, 44, 55, 66, 77, 88. Oops, that's gone too big. Right, so 86 is the biggest multiple of 11, which is 77, plus what? Plus 9. Okay. Or a better way of writing that is that 86 is some multiple of 11. Oh, sorry. Yeah, do it this way, actually. It doesn't matter which way you do it. I tend to like to say the multiple of whatever. So what multiple of 11? 7 lots is 77 with a remainder of 9. So remember, 9 is actually a remainder. When you do 86 divided by 11, gives you 9 remainder. So that's basically another way. So that's what's happened in this particular slide. We've reduced it to 9. Why? It's the remainder when you divide 86 by 11. So which gives us a quick method. If you want to reduce a number modulo another number, you just take the original one, divide it by the modulus number, and take the remainder. And notice that 0 can be the remainder. So, if I asked you to reduce 88, so reduce 88 modulo 11, you'd straight away say that 88 is 8 times 11 plus 0. There's our remainder. So 88 is congruent to 0 mod 11. So reduce 88 modulo 11 to 0 because that's what the remainder is. Okay. Well, let's you do a few examples. I'll get you to reduce 150 modulo 21, and you know, it might not be a bad idea to do something like 21, 42, 63, etc., etc. Even I do that sort of thing. So I'll give you a few minutes to do let's say a minute and a half to do that. Okay, let's stop there. I just had a look at the chat, and Josh said presumably about the encryption or the new COVID app. Yes, the new COVID app would certainly use some sort of encryption. We hope. Right. So going back to reduce 150 modulo 21. Well, basically, what's 150 divided by 21, and what's the remainder? So one way about it is we've got one lot of it, two lots of it, three lots of it. 4 lots would be 84. 5 lots would be 105. 6 lots would be 126, if I get this right. 7 lots would be 147. Well, that's clearly, if you go one more step, that'll get you up to 168, which is too big. So 150 is 7 times 100, 7 times. Seven times 21, which is 147, and 147, we need another 3. So 3 is our remainder. So 150 is congruent to 3 mod 21, if I've done my arithmetic correctly. So we've just written it out here. 150 is reduced to 3 mod 21. Now, I've got to say that this is probably pretty tedious. If, suppose I asked you to reduce 1,500 modulus 21, well, you don't want to be doing this till you get to 1,500. So what you might do is, I'll do this. Just bear with me. So here's my calculator. And let's just do the 150. So 150, let's see, we're dividing by what? 21. That's equal to, and you see how we've got you see how the answer is 7 point something. Okay, we don't care about this. All we need to know is that there's 7 lots of 21 plus a remainder. Or if we had done 1,500 divided by 21 is 71. Okay, so it'd be a different remainder. We'd have to, so let's see, 71. What is 71? What is 71 times 21? That's equal to 491. Okay, so if we go back and share, share. I've lost my. Oh, I've lost my camera. Yeah. There we go. So 1,500 divided by 21. 1,500 divided by 21 is 71 point something something something. So 71 times 21 is 1491. Okay, so that tells us that 1,500 is 1491 plus 9. Okay, what do I have to add to 1491 to get there? And that's 71 lots of 21 plus 9. So here's our multiple of 21. Here's our remainder. So up here, we've reduced 1,500 to 9. And that's a whole lot easier than going through that. Okay, which is exactly what this has done here. 1253 reduced to modulo 19. So I divided by 19, I get 65.95. This is the multiple of 19. Don't worry about the 0.95. So 65 times 19 is 1235. The difference to that to 1253 is 18. So you're really saying that 1253 is equal to 65 times 19 plus 18. There's our remainder. So 1253 is reduced to 18, modulus 19. Right, that brings us to 2 o'clock. So we break for a little bit, go get a cup of tea. The next lecture is basically doing this, reducing a number, and then there are even easier ways of doing things which will be useful. So let's break for, let's see, maybe 5 minutes. It's 2 o'clock now, so if we come back at, let's say